Michael. Good afternoon, everyone. So as Michael said, I had a brief break of 20 years, and coming back, I started up with 23 centimeters, and then I started to look into how to get on 70 centimeters with a dish. So I started to evaluate a few feeds that were quite common. And I put it on the website in December 2010. And this evaluation led to further questions. And that's what I would like to talk about this afternoon. So start up with some background. What do we want from a feed? And then go on to what basic radiating elements have we got to play with. Then I move on to how to make a useful feed of the radiating elements. What can you use? What tricks can you have to do that? Then I move on to what happens when you put the feed into a dish. And I also present a little bit about the most common dual band configuration. And finally, something about tolerances on the dimensions of a popular feed. And it's all, like Michael said, made from simulations and not from measurements. And of course it's simulations, so it's not the perfect truth, but I think it's as good as amateurs can get, as it is very difficult to measure anything at 430 megahertz on a measurement range, especially on an indoor range, and most amateurs does not have access to such equipment. So I think that the simulations are good enough. So what we want from a feed is, of course, a good illumination of the dish, so we get the gain we expect. We don't want it to radiate outside the dish, not on the sides, nor backwards. We want it to have to low loss, so we won't lose any power or get any noise into the receiver that we don't need to. And of course, minimal dimensions, so we don't make too much blockage. And of course, for mechanical reasons, weight, wind load, etc. We also need to have clean polarization properties, and that is low cross polarization radiation. We'll come to that. And also, we want to have a stable phase property as function of the illumination range across the dish to keep up the efficiency. So the basic elements is the dipole, the loop, the patch, and the annular ring. The dipole and loop are very similar indeed. The dipole and the loop, a folded dipole and the loop are not far from each other, just that you stretch it out. And the patch and the annular ring also have a relationship, as you can view the annular ring as the most outer part of a patch. So the question is, are there any fundamental differences between the properties of these feeds? Not really, as all of them has a broader radiation pattern in the H plane than in the E plane. So if you look at the dipole, all radiating elements have the same properties, more or less. So choosing what basic radiating element you want to use is up to your preferences. And some of them are easier to use if you want to use two polarizations accessible at the same time. For instance, if you like to use the IQ plus or any polarization diversity. And that would be the patch and the annular ring. The loop is very hard to feed on two places. If you have any ideas on that, please let me know. And the dipole, then you have to put up still another dipole with the other polarization. So We had a problem with that H-plane being wider than the E-plane, and that's not good when you want to feed a dish. As then you have to make a compromise between under-illuminating the dish or over-illuminating it and get noise. So one way to accomplish that is to stack two dipoles. And Peter this morning talked about the dual dipole feed that was invented in the early days. And these guys knew what they did. It's an excellent way, and the E and H plane becomes very close to each other. Another trick you can do is what Skildal presented, and that is to use a beamforming ring on the top of your radiating element. And that works well with dipoles, loops, or patches. Another way, if you have all these two, are mainly for the high directive feeds that you use for a high F over D ratio in the range of 0.4 to 0.6. If you go below that, you need a wider beam. And then you need a smaller reflector, but you still have the same problem with the E and H plane. Then you can put a baffle on the reflector, and that makes the E plane as wide as the H plane. And the baffle here can be used on these as well, and has a positive effect on backward radiation and the noise of the feed. The feed size, of course you want to have as small feed as possible, but the radiating element is determined by the wavelength, and there are methods that you can shorten the radiating elements, but they usually lead to unwanted properties like high cross-polar ratio and losses. So try to avoid that. So then the reflector is left, what you can play with. And if you're going to feed a flat dish, you need a larger reflector. Then if you're going to feed a deep dish, you can use a smaller reflector. The problem with the smaller reflector is that you get a bad front-to-back ratio. So you have to take care of that. And again, a baffle will take care of that. And we have a contradiction here that a small dish with a high F over D is a bad combination, as you need a large reflector to feed it, but then you get a lot of blockage. So for smaller dishes, it's easier to feed if they are a little bit deeper. So there are different kinds of unwanted radiation from a feed. The cross-polar radiation is the polarizations that you don't want. If you have a horizontal dipole, you want it to radiate in the horizontal plane, the horizontal polarization, not here. And that's the radiation you have in other polarizations is pure waste. So if you have a CPR of about 10 dB, you lose about 0.4 dB, both in receive and in transmit situation, as it's not useful power you get. The side lobes and back lobes, any side lobe that looks out of the dish surface will, in the received case, generate a lot of noise in your receiver. And that's not something you want. And if you have extensive back lobes, you have the same situation, that you lose power going in a direction not towards the dish surface where you want it, but in other directions, and you lose power. And the strong back lobes are more predominant at the small reflectors. As I said, a baffle on the reflector helps a lot. I tried to simulate the feed losses, but actually the feed losses on the most contemporary feeds are so low that they got lost in the accuracy of the simulations. So I believe that if you use lower resistive materials and good high-quality dielectrics and so on, most of the losses come from relays, connectors, jumpers, etc., close to the feed, rather than from the feed itself. So use common sense, and you won't have any problems with the feed losses. One phenomenon that has been discussed lately is that you get reflections from the dish back into the feed. And that is dependent on the feed gain and wavelength and the focal distance of the dish. So what do you get? Well, with a 10 dBi feed, that's typically a dual dipole feed. And a relatively small dish with a 2-meter focal distance, you're down to 13 dB of return loss coming from the dish. If you go to a larger dish, a larger FOVD, the situation is better. And if you go to a higher frequency, it's better as well. So with a linear polarized feed, as you use on 70, you will get it back in the same dipole as you transmit in. If you have a circularly polarized feed, you get it back in the reverse polarization, and destroys the isolation of your feed. Actually, so in 23, it's an isolation problem more than getting back into the transmitter. So a number of people have done work on this. Peter has made a paper on how he tuned the dual dipole feed in the dish by using a stub. Gerald reports that he moved the feed back and forth slightly and could find a position where the return loss was really good, much better. Then you have to keep track on the focal point and the face center of the dish, so you don't get losses from that. Sednek reports that going from 30 dB on the feed itself, he was lucky and got 50 dB return loss when mounting it in the feed. But anyway, if you have any additional hints on this, please tell us. There's a lot of more work that can be done on this. So, putting the dish in a feed. I made a simulation with 4 supporting legs and a dual dipole feed with circular reflector as an example. There are many possible configurations. Some people use just one support and a few wires. Others use a tripod. But I chose this configuration. So it's 4 metallic tubes, 50 millimeter, 1.6 meter long. And that was the longest metallic tubes I could get into my model before running out of memory. So it's quite memory consuming simulation phase. So what happened? Not much really. The blue curve is the reference curve. You see, smooth, nice. What you get here is a ripple, and you fill out the dips at 90 degrees on the copolar diagram. You see the cross-polar is not affected very much. It's still very, very low in the center. You get a little dip here. But it looks quite okay, actually. So you don't really have to worry about the supports, it seems. So with the use of Paul's W1GHZ's simulation program, I put in the data and simulated the efficiency you get from the reference case and from the case with the support legs. And you can see this dip in the middle of the diagram that you saw in the other picture. And actually, the efficiency just below 0.5 F/D has actually increased by 4 to 5%. So it seems like it acts like some kind of Kumar choke or something like that, these legs, and focus the radiation so you get higher efficiency. So actually it's got slightly better for some F/Ds, but no difference at the other ones. And as you can see here, the spillover has not changed at all. So it works quite okay with that configuration. I made a simulation on the most popular dual band configuration. That is dual dipole feed with a square reflector and the W2 IMU dual mode feed. I just made the outer part of it as it's cut off, so this part doesn't matter at all on 70 centimeters. And I made it with the two positions of the 23 centimeter feed on 60 millimeter above the surface and 80 millimeter above the surface. And for the 80 millimeter one, according to what I see, that would coincide better than the 60 millimeter that is commonly recommended with the phase center for the 432 feed and the 1296 feed. And here is what happened. So the blue curve is the reference. The red curve is with the 23 centimeters in place. The upper curve is for 60 millimeter, and this is for 80 millimeters above the surface. And as you can see, there is not very much happened to it. You can see there's a slight degradation on front to back ratio on the 60 millimeter one, and this side lobe rises slightly, but no big deal. And it actually confirms what many of you have found out, that this configuration with the W2 IMU horn in a dual dipole feed works very well on 70 centimeters. About 23 centimeters, I have to come back to that at a later time. So I looked into tolerances. How much difference in dimensions can you tolerate before the radiation properties are changed? So I looked at reflector size, dipole height, and dipole length. So I made a variation of plus minus 20 millimeters on the reflector radius. So plus minus 40 millimeters on the diameter. And as you can see, all curves are very, very close to each other. There is a small impact on the front to back ratio, but it's kind of plus minus 1 dB or something like that. The return loss is not affected very much. And the phase error across the dish remains very much the same. It's a slight change in absolute phase, but that doesn't matter, as it's a relative phase, the phase error that matters. So it's fairly tolerant to these tolerances. except as expected that the front-to-back ratio is slightly less with a smaller reflector and slightly better with a larger reflector. Going to the dipole height, there are also very small impact. I did it plus minus 10 millimeter on the dipole height, which would be very easy to keep. And you can hardly see any difference between the three curves, the reference and plus and minus 10 millimeters. Return loss looks very much the same. Here you can see that the absolute phase has changed, but the relative phase is very similar. So there is very small impact on the dipole height and the performance of the feed. Going to the dipole length, I used plus minus 2 millimeters on the dipole length. And here, as you can see, even smaller variation on the radiation performance. And the cross-polar is just a noise, very low, well below the copolar, so it's not a problem. And the resonance frequency moves as expected with a different dipole length. Also here we can see that the absolute phase changes slightly, but the relative phase remains the same. So, what have we learned from this? Well, if you carefully choose the feed, you can gain performance. And you can look into it. Use Doug's software to see what you get. Use Paul's software to see what performance you get. And you can catch most of the pitfalls in the choosing process. And the performance changes when you put it in a dish compared to when you have it in free space can be handled. Actually, it was much less than I expected. We have also seen that the dual band configuration that most people use works very well on 70 centimeters. And the variation in dimension for this particular feed is not a problem. And I think that this applies to most of our feeds. They are probably in the same order as this dual dipole feed when it comes to tolerances. So thank you very much. And please get on 70 centimeters. It's a challenging EME band, but I think it's very rewarding. Thank you very much.